Hello everyone. Welcome to my channel. In this video series, we are going to learn about the very basics of geotechnical engineering. This is its first chapter, which is about soil mechanics. We are starting with its first part. I hope you all enjoy it. Let's start with the introduction about soil and soil mechanics. The term soil has different meanings in different scientific fields. It has originated from the Latin word selm. To an agricultural scientist, it means the loose material on the Earth's crust, consisting of disintegrated rock with an admixture of organic matter, which supports plant life. To a geologist, it means the disintegrated rock material which has not been transported from the place of origin. But, to a civil engineer, the term soil means the loose and consolidated inorganic material on the Earth's crust produced by the disintegration of rocks, overlying hard rock with or without organic matter. Foundations of all structures have to be placed on or in such soil, which is the primary reason for our interest as civil engineers in its engineering behavior. Soil may remain at the place of its origin, or it may be transported by various natural agencies. It is said to be residual in the earlier situation and transported in the latter. Soil mechanics is the study of the engineering behavior of soil when it is used either as a construction material or as a foundation material. This is a relatively young discipline of civil engineering, systematized in its modern form by Carl von Ch-1 (1925), who is rightly regarded as the father of modern soil mechanics. An understanding of the principles of mechanics is essential to the study of soil mechanics. A knowledge and application of the principles of other basic sciences such as physics and chemistry would also be helpful in the understanding of soil behavior. Further, laboratory and field research have contributed in no small measure to the development of soil mechanics as a discipline. The application of the principles of soil mechanics to the design and construction of foundations for various structures is known as foundation engineering. Geotechnical engineering may be considered to include both soil mechanics and foundation engineering. In fact, according to Ch-1, it is difficult to draw a distinct line of demarcation between soil mechanics and foundation engineering. The latter starts where the former ends. Until recently, a civil engineer has been using the term soil in its broadest sense to include even the underlying bedrock in dealing with foundations. However, of late, it is well recognized that the study of the engineering behavior of rock material distinctly falls in the realm of rock mechanics, research into which is gaining impetus the world over. Now came to our next part, which are the applications of soil mechanics. Few of them are described here. One of the first applications is foundations. The loads from any structure have to be ultimately transmitted to a soil through the foundation for the structure. Thus, the foundation is an important part of a structure, the type and details of which can be decided upon only with the knowledge and application of the principles of soil mechanics. Second application is underground and earth-retaining structures. Underground structures such as drainage structures, pipelines, and tunnels, and earth-retaining structures such as retaining walls and bulkheads can be designed and constructed only by using the principles of soil mechanics and the concept of soil-structure interaction. Third one is pavement design. Pavement design may consist of the design of flexible or rigid pavements. Flexible pavements depend more on the subgrade soil for transmitting the traffic loads. Problems peculiar to the design of pavements are the effect of repetitive loading, swelling and shrinkage of subsoil and frost action. Consideration of these and other factors in the efficient design of a pavement is a must, and one cannot do without the knowledge of soil mechanics. At last, one of application is excavations, embankments and dams. Excavations require the knowledge of slope stability analysis. Deep excavations may need temporary support timbering or bracing, the design of which requires knowledge of soil mechanics. Likewise, the construction of embankments and earth dams where soil itself is used as the construction material, requires a thorough knowledge of the engineering behavior of soil, especially in the presence of water. Knowledge of slope stability, effects of seepage, consolidation and consequent settlement, as well as compaction characteristics for achieving maximum unit weight of the soil in situ, is absolutely essential for efficient design and construction of embankments and earth dams. The knowledge of soil mechanics, assuming the soil to be an ideal material, elastic, asteropic, and homogeneous material, coupled with the experimental determination of soil properties, is helpful in predicting the behavior of soil in the field. Soil, being a particulate and heterogeneous material, does not lend itself to simple analysis. Further, the difficulty is enhanced by the fact that soil strata vary in extent as well as in depth even in a small area. A thorough knowledge of soil mechanics is a prerequisite to be a successful foundation engineer. It is difficult to draw a distinguishing line between soil mechanics and foundation engineering. The latter starts where the former ends. The next topic which we are discussing here is soil formation. Soil is formed by the process of weathering of rocks, that is, disintegration and decomposition of rocks and minerals at or near the Earth's surface through the actions of natural or mechanical and chemical agents into smaller and smaller grains. The factors of weathering may be atmospheric, such as changes in temperature and pressure, erosion and transportation by wind, water and glaciers, chemical action such as crystal growth, oxidation, hydration, carbonation and leaching by water, especially rainwater, with time. Obviously, soils formed by mechanical weathering, that is, the disintegration of rocks by the action of wind, water and glaciers, bear a similarity in certain properties to the minerals in the parent rock, since chemical changes which could destroy their identity do not take place. It is to be noted that 95% of the Earth's crust consists of igneous rocks, and only the remaining 5% consists of sedimentary and metamorphic rocks. However, sedimentary rocks are present on 80% of the Earth's surface area. Feldspars are the minerals abundantly present, 60%, and igneous rocks. Amphibals and pyroxenes, quartz and micas come next in that order. Rocks are altered more by the process of chemical weathering than by mechanical weathering. In chemical weathering some minerals disappear partially or fully, and new compounds are formed. The intensity of weathering depends upon the presence of water and temperature and the dissolved materials in water. Carbonic acid and oxygen are the most effective dissolved materials found in water which cause the weathering of rocks. Chemical weathering has the maximum intensity in humid and tropical climates. Leaching is the process whereby water-soluble parts in the soil such as calcium carbonate are dissolved and washed out from the soil by rainfall or percolating subsurface water. Laterite soil, in which certain areas of Kerala abound, is formed by leaching. Harder minerals will be more resistant to weathering action, for example, quartz present in igneous rocks. But, prolonged chemical action may affect even such relatively stable minerals, resulting in the formation of secondary products of weathering, such as clay minerals like alite, kaolinite and montmorillonite. Clay mineralogy has grown into a very complicated and broad subject. The last topic of this video is residual and transported soils. Soils which are formed by weathering of rocks may remain in position at the place of origin. In that case these are residual soils. These may get transported from the place of origin by various agencies such as wind, water, ice, gravity, etc. In this case, these are termed transported soil. Residual soils differ very much from transported soils in their characteristics and engineering behavior. The degree of disintegration may vary greatly throughout a residual soil mass and hence, only a gradual transition into rock is to be expected. An important characteristic of these soils is that the sizes of grains are not definite because of the partially disintegrated condition. The grains may break into smaller grains with the application of a little pressure. The residual soil profile may be divided into three zones. First one is the upper zone in which there is a high degree of weathering and removal of material. Second one is the intermediate zone in which there is some degree of weathering in the top portion and some deposition in the bottom portion. And the third is the partially weathered zone where there is the transition from the weathered material to the unweathered parent rock. Residual soils tend to be more abundant in humid and warm zones where conditions are favorable to chemical weathering of rocks and have sufficient vegetation to keep the products of weathering from being easily transported as sediments. Residual soils have not received much attention from geotechnical engineers because these are located primarily in undeveloped areas. In some zones in South India, sedimentary soil deposits range from 8 to 15 m in thickness. Transported soils may also be referred to as sedimentary soils since the sediments, formed by weathering of rocks, will be transported by agencies such as wind and water to places far away from the place of origin and get deposited when favorable conditions like a decrease of velocity occur. A high degree of alteration of particle shape, size, and texture as also sorting of the grains occurs during transportation and deposition. A large range of grain sizes and a high degree of smoothness and fineness of individual grains are the typical characteristics of such soils. Transported soils may be further subdivided, depending upon the transporting agency and the place of deposition. First one is alluvial soils, which are soils transported by rivers and streams. Examples are sedimentary clays. The second one is eeling soils. These are soils transported by wind. Examples are loess. The third one is glacial soils, which are soils transported by glaciers. An example is the glacial till. Fourth one is lacustrine soils. which are soils deposited in lake beds. Examples are lacustrine silts and lacustrine clays. The last one is marine soils, which are soils deposited in seabeds. Examples are marine silts and marine clays. Soil may be broadly classified as coarse-grained soils, with an average grain size greater than 0.075 mm. Examples are gravels and sands. Second one is fine-grained soils, with an average grain size less than 0.075 mm. Examples are silts and clays. These exhibit different properties and behavior, but certain general conclusions are possible even with this categorization. For example, fine-grained soils exhibit the property of cohesion, bonding caused by intermolecular attraction, while coarse-grained soils do not. Thus, the former may be said to be cohesive and the latter non-cohesive or cohesionless. Further classification according to grain size and other properties is given in later chapters. Thank you for staying with us in this video. Please like this video and subscribe to our channel for upcoming civil engineering related videos. In the next video, we are going to discuss about the structure and texture of the soil. See you soon. Thanks for watching.